Let us now talk a little bit about the properties of the Z transform. The first property is linearity. If you have two sequences, discrete time signals, x1 of n and x2 of n, with the respective regions of convergence, ROC1 and ROC2 in the Z domain, the linear combination of these two signals will result in a Z transform, which is a linear combination of the Z transforms of individual signals. And the region of convergence will be the intersection of the two regions of convergence. So the second property is time shift. So if we shift our signal by k samples, its Z transform will be multiplied by z to the power minus k. So there's a little typo in here. Let me just correct this. This has got to be k, z to the power minus k. Okay, and the region of convergence will be equal to the region of convergence of the original signal. Now, this is a very important property which we're going to use quite a lot when we're dealing with signals and systems in the Z domain. The third property is scaling in Z domain. So if you multiply a signal by an exponential sequence, a to the power n, which depends on the time index of that signal, the Z transform of the new signal will be scaled version of the Z transform of the original signal. So we have x of a to the power minus 1 z as our new Z transform. So if the original region of convergence was a ring between R1 and R2, between two radii R1 and R2, then the region of convergence for the second signal, the scale signal, would be R1 less than A1, A to the power minus 1, Z less than R2. Okay, so this is scaling in Z domain. Then another property is time reversal. So if you get the mirror image of your signal with respect to the time origin, n equals to 0, then the Z transform will be the mirror polynomial of your signal. That is the same polynomial coefficients, but the term is not z anymore, it's z to the power minus 1. So you substitute z to the power minus 1 everywhere you see z in that case. So if the region of convergence for the first sequence was a ring between R1 and R2, then region of convergence for the second signal would be R1 less than absolute value of z to the power minus 1 less than R2, which means if we wanted to write it down in terms of z, we would have 1 over R2 less than absolute z less than 1 over R1. And yet another property is derivative in the Z domain. The relation is a little bit, well, it's not too tricky, but it's just a little bit tricky to show. Why do we have that kind of a relation between the derivative of x of z and x of n? So let's show how this works out. If you want to express the direct Z transform, x of z, so let's write it down. Well, as a matter of fact, it doesn't have to be n equals to 0, it can be any n, okay, for any n, x of n, z to the power minus n, so this is our direct Z transform, and we want to get the derivative with respect to z, so d over dz of x of z is equal to what? It is equal to, for all n minus n, times x of n z to the power minus n plus 1. Right? And if you want to write it in a simpler way, we can just factor out the z as well, which means we have a z transform that is in this form minus z to the power minus 1 times for all n xn z to the power minus n. So we now have a new sequence nx of n, which is going to show us that the z transform of n x of n is minus z d over dz x of z. And since we are dealing with a polynomial, possibly with an infinite order, the regions of convergence will be the same between the derivative in signal whose z transform we're taking derivative of, and the original signal x of n. So let's make this a little bigger to make it more visible. All right, so far so good. Now let's have a look at the convolution of two sequences. We have x1 of n and x2 of n. We convolve them, and the z transform is the product of two z transforms, x1 of z and x2 of z. And the region of convergence will obviously be the intersection of region of convergence 1 and region of convergence 2. Now, this is, again, a very important property which will allow us to find out how combinations of systems behave, and it makes things easier to work with in the Z domain. So let's show how we obtain this. So let's first write the convolution of x1 of n and x2 of n as y of n. So x1 of n convolved with x2 of n. So let's write this as a convolution sum, if you like. And if you remember from last week, this is x of k, x1 of n minus k, x2 of k. Right? So this is the, for you to remember, this is the convolution sum. Okay, so we're going to move forward and get the z transform of this. So y of z is equal to y direct z transform for all n, y of n, z to the power minus n, which is equal to, now we are going to just substitute the line above, the convolution sum into this. So for all n, and then for all k, x1 of n minus k, x2 of k, z to the power minus n. That's good. So we're just going to factor out z to the power minus k from the z term here. So let's write it down as this. For all n and for all k, we're getting the sum x1 of n minus k, x2 of k, z to the power minus k times z to the power minus n minus k. Okay, so we have done, nothing important, by the way. We just factored out z to the power minus k so that we can express this sum as in terms of the same time indices for x2 of k and x1 of k, n minus k. Okay, and you can see that since we're taking all n in this case, we have the product of x1 of z and x2 of z. And obviously, if any one of these series diverges, any one of these z transforms diverges, then the whole thing is going to diverge, which means we're dealing with the intersection of the two regions of convergence in this case. Okay, so finally, we are at the cross correlation of two sequences. So we have x1 of n convolved with x2 of minus n in this case, and the z transform would be the product of x1 of z and x2 of z to the power minus 1. Since we're dealing with convolution, this is easier to see because we have already showed that the convolution ends up as a product in the z domain. And the region of convergence is, again, an intersection of two regions of convergence. First of all, since for this z transform to converge, the first term, x1 of z, has to converge. We need to have this in place. And for the second one to converge, this to converge, we have ROC2 prime. That is the reciprocal region of convergence to be there as well. So ROC2 prime then is the region of convergence of x2 z to the power minus 1. So that is the reciprocal of x2 of z, the region of convergence for x2 of z. Okay, so these are some properties. There are many other properties, but we're not covering all of it. That brings us to rational z transforms. You typically see z transforms in this form, especially if you're dealing with an IIR system or any type of recursive system, really. You end up with a z transform of this form. And if you want to write this rational form in here, okay, so if you want to write this in open form, we end up with this expression. And if we divide the numerator by z to the power minus m, so if we are dividing this polynomial by z to the power minus m and this polynomial by z to the power minus n, we end up with an expression which looks like this. So this is multiplied by the second term. Okay, so we have one term which is the ratio of b0 z to the power minus m and a0 z to the power minus m, and the second term which has two polynomials, a numerator polynomial, an mth order numerator polynomial, and nth order denominator polynomial. Okay, and we can then ask the question, how many roots do each of these polynomials have? Now, in the first example, we have a ratio of two monomials. We have single-term polynomials, that is. So the first one we can write perhaps in a simpler way. So let's write it that way. So the first term is then b0 over a0. It's just a constant term. Z to the power minus m minus n. And the second term we're going to write as a ratio of two products. So k from 1 to m, z minus z to the power, z sub k over another product, k from 1 to n this time, z minus p sub k. So z sub k for all k from 1 to m are zeros, are the zeros of this form, and p sub k, again for all k from 1 to n, are the poles. Now, why are they called this way? Why zeros and poles? That is because when we we evaluate the Z transform at any one of these zk's, the numerator polynomial will be 0, which means the whole Z transform is going to be 0 unless you have the same 0 as a pole in the denominator polynomial. And why? Well, 0 is kind of clear. And why do we call the denominator polynomials roots as poles? Think about a circus tent where there is a pole holding the whole tent together. Think about the shape that has. Closer and closer to the pole position, you're going to have higher and higher values. Right? That is why the denominator roots are called the poles. We haven't yet seen the magnitude response, but when we look at the magnitude responses of systems at frequencies close to pole positions, we're going to have larger values. So that is why they're called poles. Okay, so how about the first part? Just write it with blue color about this first part. So if n is greater than m, that is the denominator order is greater than the numerator order, then we have absolute value of m minus n, or n minus m, doesn't matter too much, m minus n, zeros at the origin. What else? So these are repeated zeros at the origin. And if n is less than m, we have again m minus n absolute poles at the origin. Okay, so so far so good about rational Z transforms. Let's see two examples about this. The first example, we have a signal which looks like an exponential signal, a to the power n, but it has a finite time support. Only m values of our signal is non-zero. How do I see this? We have two step signals, right? The first step signal u of n, so let's try to see how it works. So u of n looks like this. I use, okay. So it's all zeros up until n equals to 0, and after that it's all ones. Okay, so this is 0, 1, 2, 3, and this is 1. So this is n. And let's have a look at the time-shifted version of this. We shift it by m samples. So we may remember from last week that if we shift our signal by m samples, it's going to start later, right? So this is n as well. So let's just see how we represent it. It's all, if m is positive, it's all zeros up until some m minus 1, and at the mth time index we have a 1, and after that it's all ones. Okay, so this is nice. What we do then is subtract the second sequence from the first sequence, which means we're going to end up with a sequence which has a kind of like a rectangular shape. So probably I don't need to draw it. But anyway, so imagine a rectangular pulse which is discrete time, which has the value 1 from 0 to m minus 1, and after that it's 0. And we multiplied this by a to the power n. So this is that kind of a signal. Okay? Maybe we can just draw x of n here, just to make clear how it looks like. So this is x of n, and this is n. Okay, so it starts at 1, then a squared, a cubed, etc., and a to the power m minus 1. So a cubed, a squared, a to the power 1. So it exponentially decays up until a to the power m minus 1. Then it's 0. So it has a finite time support. Okay, so this is our signal, right? And a is greater than 0. Yeah, so it doesn't matter which value that is, as long as the Z transform converges. But let's have a look at the Z transform of this signal. Okay, so let's write x of z. So we're going to use the direct Z transform again. That is for n from 0 to infinity, a to the power n, z to the power minus n, minus n from m to infinity, a to the power n, z to the power minus n. Or, equivalently, n from 0 to m minus 1, a to the power n, z to the power minus n. Okay, so this is our direct Z transform for the signal. All right, so what do we have then? The Z transform of the first term is, if it converges anyway, it is 1 over 1 minus a z to the power minus 1. And for the second term, you can just show it by factoring out some of the terms. You can just show it that the Z transform is a to the power m, z to the power minus m, 1 over 1 minus a z to the power minus 1. And finally, the third term, that is what we're after, has a form 1 minus a z to the power minus 1 to the power m over 1 minus a z to the power minus 1. Or equivalently, we have, so let's just write minus here, let's just put an equals sign here. So finally, we end up with, if we just divide both the numerator and denominator by z to the power m, we're going to have this kind of a z transform, z to the power m minus a to the power m over z to the power m minus 1, so we've divided both, and z minus a. So for the denominator, it is somewhat easy to find out where the roots are. So we have, so let me just write it here, we have one pole at, so we're looking at values of z which make the denominator 0, which is going to cause the whole thing to diverge. So we have one pole at z equals to a, and m minus 1 poles at z equals to 0. Okay, that is nice. So then the question is, what are the zeros of the second sequence? So let's have a look. So for the denominator, we have one root at z equals to a, and m minus 1 roots at z equal to 0. So these are called poles. We have discussed this already. And for the numerator, we have to set this polynomial, z to the power m minus a to the power m, to 0. Okay, so obviously z equals to a is one solution of this, but what other solutions do we have? We need to remember that z is a complex number. And when z is a complex number, we can just very simply remember something which is important. So let's write that as a note here. So e to the power j 2 pi k is equal to 1, right? When k is an integer. That is why, because we have cosine 2 pi k plus j sine 2 pi k, and since sine 2 pi k is always 0 and cosine 2 pi k is always 1, we have this expression equal to 1. So what then are the roots of this second polynomial, z to the power m minus a to the power m then? Then the roots of that polynomial, zk, is equal to a e to the power j 2 pi k over m, because when you get the mth power of this, you're going to end up with a to the power m, irrespective of what k you have. So in this case, so this is pi, if you have trouble seeing it, and for k from 0 to m minus 1. So we have m zeros then. So for k equals to 0, we have zk equals to a, and then all the remaining zeros are around the unit circle. So we have then x of z equals to, for all k, z minus a e to the power j 2 pi k over m, and when we say for all k, we mean So let me just write it once again. Sorry about this. Yeah. So x of z is then again for k from 0 to m minus 1, z minus a e to the power j2 pi k over m over z to the power m minus 1, z minus a. Now you can see that when k equals to 0, we have a 0 at z equals to a as well, so these two cancel out, which means the final form is of this form. We have m minus 1, zeros and m minus 1 poles. So this is k from 1 to m minus 1, z minus a e to the power j2 pi k over m over z to the power m minus 1. And if you want to draw the zeros and poles of the system, so let's use red for the zeros. We have a 0 at z equals to a, and all the rest are equally spaced around the unit circle, around the circle which has a radius a. And these are going to be at complex conjugate positions. So if a plus jb is a root, then a minus jb is also going to be a root. So these are the zeros, and let's draw the poles as well. So we have one pole at z equals to a and m minus 1 poles at 0. And since these two are going to cancel out, we're going to have m minus 1 poles and m minus 1 zeros effectively. So these are going to cancel out. Cancels out. Okay? So this is an example for the roots of a rational Z transforms. Now, the question then you may ask is what happens, for instance, if you move the poles close to the unit circle? And we have a Python example in the Python notebook that I'm making available on Binder. So you will be able to use it and see for yourself what happens when you move the poles closer to the unit circle. Okay, so let's have a look at how we represent system transfer functions in terms of Z transforms. Now, first of all, for any system whose impulse response we know as h of n, as long as the Z transform converges, we can write it in the Z domain in this form. This is just a direct Z transform, right? We have seen many examples of this within this video. And we can define two different types of systems. The first type of system is the finite impulse response, or FIR system, and the second type of a system is an IIR system, that is a system which has an infinite time support. So it has values, it has non-zero values for all n. Okay, so let's have a look at the first example. So let's say we have finite impulse response system, which is also causal. There's nothing that prevents our system from being causal. So let's say the Z transform, sorry, I'm going to write it in blue, age of Z is equal to k from 0 to m b sub k z to the power minus k. Now, by the way, z sub k is the value of the impulse response at the kth sample. So b sub k is equal to this. Okay, that's nice. And we can also continue expressing this in this form. If you factor out z to the power minus m, we have this form, z to the power m, and k from 0 to m b sub k, z to the power m minus k. So we have a polynomial with positive exponents only now. But then we also have a denominator polynomial, which means we have a system which has all of its poles at z equals to 0. So this is our poles. All poles are at z equals to 0. And the zeros are just the roots of this second polynomial. Okay? Despite having m poles at 0, this system is called an all-zero system because it's an FIR system. And it has all of its meaningful, let's say, zeros at and no, poles except at 0. All right, so IIR systems, infinite impulse response systems. There are different types of this, but we're just going to give a single example. So we can write the Z transform, h of z, the transfer function of our system, as, again, this is just one example, so you may have many different types of IR transfer functions, but so let's write it down as this, k from 1 to n, so let's say an nth order polynomial, denominator polynomial a sub k, z to the power minus k, and let's divide both the numerator and the denominator by z to the power n, so that we have b0 z to the power n. Sorry, we're dividing both numerator and denominator by z to the power minus n, not z to the power n. And the denominator polynomial becomes k from 0 to n a sub k z to the power n minus k. But since in the original form the first coefficient is 1, we have to make sure that a0 is 1, okay, in this form. Again, we can have many different types of IIR systems. We can have all poles system like this one, or we can have pole zero systems, which has both zeros and poles, which can eventually be represented as a cascade of two IR filters or two IR systems, which are all poles and all zero systems. Okay, so this is an example of an IR system. And just before we move on to inverse Z transforms, I need to write the correct term for this. This is the transfer function. So when anyone says transfer function, you will have to immediately remember that it is the Z transform of the impulse response of the system.